Mount Baker rises through the clouds of the northern Cascade Range like a volcano that forgot how volcanoes are supposed to behave. Its summit is buried beneath thick ice. Steam leaks quietly from Sherman Crater. Glaciers grind across fractured volcanic rock. Rivers carry sediment down valleys lined with forests and towns. On the surface, it often looks calm enough to ignore. Yet deep beneath the mountain, something refuses to stay fully asleep. Why does one of the quietest volcanoes in North America still produce deep earthquake signals linked to fluids and magma? Why did scientists in the 1970s watch the mountain suddenly heat up without erupting? Why does Baker produce so little shallow seismic unrest compared with volcanoes like Mount St. Helens? And why are volcanologists increasingly worried that the mountain's glaciers may hide and sometimes distort the warning signs normally used to forecast eruptions? These questions have turned Mount Baker into one of the strangest volcanic systems in the Cascade Arc. Not because it erupts constantly, not because it produces giant ash columns every decade, but because it breaks the expected relationship between magma, earthquakes, deformation, and surface activity that volcanologists rely on to understand dangerous volcanoes. Most volcanoes follow patterns: magma rises, rock fractures, swarms of volcano-tectonic earthquakes shake the crust, the ground inflates, gas emissions increase, heat flow rises, pressure builds. The system announces itself through escalating unrest before eruption becomes possible. Mount St. Helens demonstrated this dramatically before the catastrophic eruption of 1980. Even Mount Rainier, despite its long quiet periods, maintains a restless seismic background tied to its enormous hydrothermal system and unstable volcanic structure. Mount Baker often does not cooperate with those rules. The mountain can remain seismically quiet for long periods while still producing persistent hydrothermal activity and deep, long-period earthquakes that suggest fluid movement far beneath the volcano. That disconnect has become one of the most important mysteries in Cascade volcanology. To understand why Baker behaves this way, scientists first have to understand the tectonic engine powering the entire Cascade volcanic chain. The Cascades exist because the small oceanic Juan de Fuca plate is descending beneath the North American plate along the Cascadia subduction zone. As the oceanic slab sinks into the mantle, increasing temperature and pressure release water and volatile compounds trapped within hydrated minerals. Those fluids rise into the overlying mantle wedge, lowering the melting temperature of mantle rock and generating magma. That magma does not travel upward in a single clean column. Instead, it stalls, cools, crystallizes, remelts, mixes with surrounding crustal rock, and migrates through networks of fractures and reservoirs over thousands to hundreds of thousands of years. Some magma reaches the surface and erupts. Much of it does not. Volcanoes are therefore not simple pipes connected directly to molten chambers. They are dynamic plumbing systems spread across large regions of crust. Recent research across the Cascades has strengthened the idea that long-lived partial melt zones may persist beneath volcanoes even during long, quiet intervals. Scientists increasingly believe many Cascade volcanoes contain crystal-rich magma reservoirs that survive far longer than previously assumed. These systems may contain partially molten rock capable of reactivation even when obvious eruption signals are absent. That idea is especially important for Mount Baker. Baker's behavior suggests that magma can remain present at depth without producing the intense shallow seismic activity commonly associated with eruptive unrest. Instead of frequent brittle rock fracture earthquakes near the surface, Baker produces deep, long-period earthquakes occurring roughly 9 to 19 miles deep, or about 15 to 30 kilometers beneath the volcano. These deep, long-period earthquakes are fundamentally different from ordinary tectonic earthquakes. Traditional earthquakes occur when stress accumulates until rock suddenly breaks along faults. Deep, long-period events instead appear connected to movement of fluids, gas-rich magma, or pressurized volatile phases within deep crustal environments. Their waveforms are lower frequency and more emergent than sharp brittle failure earthquakes. What makes Baker unusual is not merely the existence of deep, long-period events. Other volcanoes produce them too. The mystery is that Baker produces significant deep signals while remaining remarkably quiet in the shallow crust above. In many volcanic systems, deep magma recharge eventually transfers stress upward, fracturing rock as magma intrudes into shallower levels. That process generates the classic volcano-tectonic earthquake swarms used in eruption forecasting. At Baker, the deep system often appears partly disconnected from the shallow crustal response. Scientists think several mechanisms may explain this. One possibility involves the physical state of the crust beneath Baker. If portions of the crust are already heavily fractured, hydrothermally altered, or thermally weakened, fluids may migrate upward without generating large, brittle failure earthquakes. Instead of violently cracking intact rock, fluids could exploit existing permeable pathways. Another possibility involves magma flux. Baker may receive relatively small pulses of magma that inject heat and volatiles into the system without accumulating enough pressure to force rapid ascent toward the surface. In this scenario, magma recharge occurs incrementally over long timescales, sustaining hydrothermal circulation while rarely escalating into eruption. The 1975 Sherman Crater unrest episode became one of the clearest demonstrations of this strange behavior. During that period, observers noticed increasing fumarolic activity and rapid melting of ice within Sherman Crater near Baker's summit. Steam emissions intensified dramatically. New thermal areas formed. Heat flow increased. The hydrothermal system appeared to awaken suddenly. Under normal volcanic forecasting logic, scientists would expect significant accompanying seismic unrest if magma were intruding upward. Yet Baker produced surprisingly little shallow earthquake activity during the crisis. The absence of major seismic swarms created immediate uncertainty. Was magma actually moving beneath the volcano? Or was the hydrothermal system changing independently through non-magmatic processes? Subsequent analysis suggested a relatively small magma intrusion probably occurred at depth, injecting heat into the hydrothermal system without triggering eruption. Instead of ascending rapidly toward the surface, the intrusion may have stalled deep enough to avoid catastrophic failure of the upper volcanic edifice. That interpretation fundamentally challenged simplistic eruption models. Baker demonstrated that magma intrusion does not always lead to eruption, and that hydrothermal crises can develop with minimal classical warning patterns. The hydrothermal system itself plays a major role in Baker's unusual behavior. Hydrothermal systems form when groundwater circulates through hot volcanic rock. Water descends through fractures, heats near magma or residual heat sources, then rises back upward, carrying dissolved gases and minerals. Over time, this circulation chemically alters surrounding rock. Strong volcanic acids generated from sulfur-rich gases transform hard lava into weak clay-rich material through hydrothermal alteration. This process matters enormously because altered volcanic rock becomes mechanically unstable. Instead of strong, coherent lava flows, portions of the volcano gradually weaken into collapse-prone slopes. Mount Baker is heavily glaciarized, meaning enormous masses of moving ice rest directly atop these altered volcanic materials. Baker contains one of the greatest concentrations of glacial ice in the Cascade Range. Ice thickness, meltwater flow, and glacier motion all interact continuously with the volcanic structure beneath. This glacier-volcano interaction has become one of the fastest-growing areas of Baker research. For decades, scientists struggled to interpret certain shallow seismic signals around the volcano. Some events resembled volcanic earthquakes. Others appeared seasonal. Many lacked clear signatures. Increasingly, researchers realized glaciers themselves generate complex seismic activity. Glaciers are not static bodies of frozen water. They deform internally, fracture, slide across bedrock, and channel meltwater through pressurized subglacial drainage systems. Each of these processes generates seismic energy. Icequakes, basal slip events, crevasse formation, and turbulent meltwater transport can all produce low-frequency seismic signals capable of mimicking volcanic unrest. This emerging field, known as cryoseismology, has forced scientists to reinterpret parts of Baker's seismic record. Some shallow low-frequency events once suspected to indicate magma movement now appear linked to glacier dynamics instead. Seasonal melt cycles strongly influence seismic noise around the volcano. During warmer periods, increased meltwater lubricates glacier beds and alters stress conditions within the ice mass. That creates changing seismic patterns unrelated to volcanic eruption processes. This overlap creates a major monitoring problem. At volcanoes like Mount St. Helens, frequent shallow earthquake swarms often provide relatively clear evidence of magma ascent. At Baker, glacier-generated seismic noise can partially obscure subtle volcanic signals. The volcano essentially hides behind its own ice. That challenge may become even more serious as climate change accelerates glacier retreat across the Cascades. At first glance, shrinking glaciers might seem like they would reduce volcanic hazards. Less ice should mean less meltwater available for lahars and fewer glacier interactions overall. But the geology is far more complicated. Glaciers exert enormous pressure on volcanic slopes. As they retreat, stress distributions within the mountain change. Previously ice-supported rock faces become exposed and destabilized. Hydrothermally altered rock hidden beneath glaciers may suddenly collapse once ice buttressing disappears. Retreating glaciers also reorganize meltwater pathways. Water infiltrates new fractures, alters pore pressure conditions, and changes erosion patterns along steep slopes. These hydrologic changes can destabilize volcanic terrain even without eruption. At Baker, scientists are increasingly concerned that glacier retreat could expose weakened rock zones surrounding Sherman Crater and other hydrothermally altered areas. Rockfalls, debris avalanches, and glacier outburst floods may become more common as ice cover thins. This matters because Baker's greatest hazards may not come solely from explosive eruptions. Like Mount Rainier, Baker possesses the ability to generate lahars, fast-moving volcanic debris flows composed of water, mud, rock, and volcanic sediment. Lahars can travel enormous distances along river valleys at terrifying speed. Unlike lava flows, lahars behave more like flowing concrete. They can uproot forests, bury infrastructure, destroy bridges, and overwhelm valleys far downstream from the volcano itself. Baker's extensive glaciers provide abundant water sources capable of feeding such flows during eruptions, slope collapses, or rapid melting events. Even relatively small eruptive activity interacting with thick summit ice could trigger dangerous debris flows. Yet Baker differs sharply from Rainier in terms of overall hazard structure. Mount Rainier towers above densely populated valleys connected directly to major metropolitan regions. Its hydrothermally altered core and immense ice volume make it one of the most dangerous volcanoes in North America from a lahar perspective. Ancient events like the Osceola mudflow demonstrated the scale of collapse possible at Rainier. Baker is smaller and drains into less populated regions, but geologically, the underlying processes remain similar. Hydrothermal weakening, glacial loading, unstable slopes, and meltwater interactions all create the conditions for large sediment-rich flows. What separates Baker scientifically is not necessarily its hazard magnitude, but the ambiguity of its warning signs. Volcanologists rely heavily on patterns. The more a volcano behaves according to established eruption sequences, the easier it becomes to forecast dangerous changes. Mount St. Helens has become one of the best-studied volcanic systems on Earth, precisely because its activity generates measurable and repeatable monitoring signals. Before eruptions, St. Helens commonly produces strong earthquake swarms, deformation, gas release, and thermal anomalies. Magma ascent there tends to announce itself clearly. Baker often remains cryptic. The deep, long-period earthquakes suggest magma or fluids continue moving beneath the volcano. Hydrothermal activity persists. Heat escapes continuously through fumaroles, yet shallow crustal unrest often remains muted. This raises a profound scientific question. Can some volcanoes maintain partially molten systems for centuries while producing only weak surface signals? Increasing evidence suggests the answer is yes. Modern imaging studies across volcanic arcs increasingly reveal that magma reservoirs are not giant liquid chambers waiting to erupt. Instead, many are crystal-rich mush zones containing varying fractions of melt distributed through broad regions of crust. These mush systems may evolve slowly, periodically recharged by deeper magma injections. In such systems, eruptibility depends not merely on the presence of magma, but on melt connectivity, volatile accumulation, temperature evolution, and pressure conditions. A volcano can therefore contain magma without being eruption-ready. Baker may represent an extreme version of this state. Instead of cycling rapidly between eruption and dormancy, the volcano may spend long periods in a partially active thermal condition where heat and fluids continue migrating upward without large-scale magma ascent into shallow crust. That interpretation aligns with the deep long-period earthquake observations. These events may represent fluid migration through deep crustal pathways connected to slowly evolving magma reservoirs. But uncertainty remains enormous. Scientists still do not fully understand what triggers transitions from quiet magma storage to eruptive instability. Nor do they fully understand why some intrusions stall harmlessly while others evolve into explosive eruptions. Part of the difficulty comes from the physics of magma itself. Magma is not a simple liquid. Its behavior changes dramatically depending on temperature, crystal content, dissolved gases, viscosity, and surrounding pressure. Gas-rich magma can remain relatively stable at depth where high pressure keeps volatiles dissolved. As magma rises, pressure decreases, allowing gases to exsolve into bubbles. That transition can radically increase internal pressure and explosivity. In silica-rich stratovolcanoes like Baker, viscous magma traps gases efficiently. Pressure can accumulate until fragmentation occurs, producing explosive eruptions capable of generating ash columns, pyroclastic flows, and lateral blasts. Yet if magma cools or crystallizes before reaching shallow levels, eruption may never occur. Heat may instead transfer gradually into surrounding hydrothermal systems, producing fumarolic unrest without magma eruption. That appears to be close to what happened during the 1975 episode. The event became a warning to volcanologists not to oversimplify volcanic unrest. Heat transfer alone can destabilize hydrothermal systems dramatically. Ice melt increases. Steam explosions become possible. Slope instability rises. Yet magma may remain too deep or too limited in volume to erupt. This ambiguity complicates hazard communication enormously. When a volcano like St. Helens produces escalating seismic swarms and deformation, officials can more confidently raise concern levels. At Baker, scientists may observe subtle changes whose significance remains unclear even to experts. Deep, long-period earthquakes particularly complicate interpretation because they do not necessarily indicate imminent eruption. Some volcanoes produce them for decades without erupting. Others experience them shortly before major unrest. The physical mechanisms behind these events remain actively debated. Some researchers argue they reflect movement of magmatic fluids through deep fracture networks. Others propose resonance within fluid-filled cracks. Still others suggest interactions between supercritical fluids and partially molten crust. Supercritical fluids themselves represent another fascinating aspect of volcanic systems. At sufficiently high temperature and pressure, water enters a supercritical state where distinctions between liquid and gas disappear. These fluids possess extraordinary capacity for transporting heat and dissolved minerals. Within volcanic crust, supercritical fluids may migrate efficiently through fracture systems, redistributing thermal energy over large distances. If such fluids exist beneath Baker, they could help explain why hydrothermal activity persists despite limited shallow seismicity. The hydrothermal system therefore becomes not merely a surface feature, but part of a deep interconnected thermal engine linking magma, fluids, rock mechanics, and glaciers into a single evolving system. Even the glaciers themselves may influence volcanic behavior more than previously recognized. Ice loads exert substantial pressure on volcanic edifices. Changes in glacier thickness alter stress fields within underlying rock. During deglaciation after the last ice age, many volcanic regions worldwide experienced increased eruption rates, possibly because unloading reduced confining pressure on magma systems. Modern glacier retreat occurs on smaller scales, but similar principles may still matter. Reduced ice loading could subtly alter fracture conditions, permeability, and magma ascent pathways over long timescales. At Baker, where glaciers remain extensive but rapidly changing, these interactions are especially important. The mountain essentially exists at the intersection of volcanology, hydrology, glaciology, tectonics, and climate science. Few cascade volcanoes integrate so many active geological systems simultaneously. That complexity is precisely why scientists continue watching Baker so closely despite its long quiet periods. The volcano violates assumptions. It shows that low seismicity does not necessarily mean geological inactivity. It shows that magma can remain hidden beneath apparently calm volcanoes. It shows that glaciers can disguise volcanic signals while simultaneously amplifying volcanic hazards. And it shows that hydrothermal systems can destabilize dramatically without culminating in eruption. For volcanologists, Baker has become less a conventional eruptive system and more a natural laboratory for understanding subtle volcanic processes operating below the threshold of eruption. The scientific importance of this cannot be overstated. Most volcanic monitoring systems worldwide were developed around relatively obvious unrest patterns. But if some volcanoes behave more like Baker, maintaining deep thermal activity while producing weak surface indicators, then eruption forecasting may require entirely new approaches. Future monitoring increasingly depends on integrating multiple disciplines simultaneously. Seismology alone is insufficient at Baker because glacier processes complicate interpretation. Ground deformation measurements help track subtle crustal changes, but deformation may remain weak during deep intrusions. Gas chemistry provides clues about magma degassing, yet hydrothermal systems can modify gas signatures before they reach the surface. Scientists therefore combine seismic analysis, satellite radar deformation mapping, thermal imaging, gas monitoring, glacier motion studies, and hydrologic observations to build a more complete picture. Even then, uncertainty remains unavoidable. Volcanoes are not machines with predictable outputs. They are evolving thermodynamic systems governed by nonlinear interactions between rock, melt, fluids, stress, and temperature. Small changes deep underground can produce disproportionately large consequences at the surface, or no visible consequences at all. Mount Baker embodies that uncertainty better than almost any volcano in the Cascades. It is neither fully dormant nor clearly active, neither silent nor loudly restless. It occupies an uncomfortable middle ground where deep geological processes continue operating beneath a deceptively calm exterior. That is what makes the volcano scientifically unsettling. The public often imagines dangerous volcanoes as mountains constantly erupting smoke and lava. Baker rarely behaves that way. Its danger comes partly from subtlety. Quiet systems can be misunderstood. Weak seismicity can create false confidence. Glacier-covered slopes can conceal instability until collapse begins. And beneath the ice, beneath the fumaroles, beneath the fractured volcanic rock, the deeper system continues evolving in darkness far below the surface. The deep, long-period earthquakes continue. Fluids continue migrating through crustal pathways. Heat continues escaping through Sherman Crater. Glaciers continue grinding across hydrothermally altered slopes. And somewhere beneath Mount Baker, magma likely still exists, not erupting, not disappearing, but waiting inside one of the strangest volcanic systems in North America.